Hello and welcome to another one of D's ADD videos. Today we're going to be looking at the concept of valence bond theory and hybridization. Basically what we're doing here is we're looking at the reactivity of the electrons in the valence shell. If you remember, the electrons determine the reactivity in the atoms and the protons determine the identity. So the compounds found in nature would not be able to bond and form the angles we find observed if the electrons stayed purely in their respective orbitals. There's a lot of unexpected bond angles, a lot of unexpected number of bonds. So to form a bond, an atom needs to donate an electron, and the first bond that's formed is a sigma bond. All those things that we've been drawing in the Lewis structures, the single bonds were all sigma bonds. And it's basically a increased electron density or probability of finding an electron between the nuclei of the atoms. And it forms a bond between these two atoms and is the foundation for a double and a triple bond as well. So double and triple bonds have extra pi bonds in which they're unhybridized p orbitals that have an unpaired electron overlap. Double bonds have one sigma and one pi bond, whereas triple bonds have one sigma and two pi bonds. To account for all the varied unexpected bond angles and the types of bonds and the number of bonds that atoms could make, chemists theorized that the orbitals were merging and exhibiting characteristics of both. So an sp hybridization would have some s character, spherical character, and p character, or the dumbbell shape. Now there's an easy way to do this and there's a hard way to do this. Of course, most people want to know the easy way, and the easy way to look at this is to memorize, based on the number of domains found in the Lewis structure, the hybridization that you see. So if you're not very proficient in your Vesper and your Lewis structure, you need to be by now, and it will affect your hybridization knowledge. What you need to do is memorize this table, okay? If nothing else, it'll help you check your work. Based on the number of domains, we have these hybridizations. So if we have two domains being bonded to the central atom, it's sp. If we have three domains, it's sp2, 4, sp3. Then we run out of orbitals in the p subshell, so then we go to the d. 6 is sp3d2. All right, so if you look, you can see a pattern that the number of domains is always one more than the exponent for your p. Until we run out of the p's, then we start going to the d's. So there's one extra, so we go to the d, two extra, and we go to the d. Now what is the long way? Well, the long way is we have to use orbital diagrams to visually display the sharing of the electrons in the valence shell and the hybridization that occurs. Let's look at methane, for instance. Methane is just a simple sp3. If you don't know that, just by looking at this by now, you need to go back and practice. It's got 4 bonding domains. It's going to have 8 valence electrons, all of which are going to be bonding electrons. So with 4 domains, we know automatically it's sp3, but let's look at what's going on here. Typically I don't do an example problem in here, but I think it's good for this scenario because it's a little vague otherwise. So carbon needs 4 unpaired electrons in order to form a sigma bond with one of each of these hydrogens. And if we use off-bound Hund's rule, this is what your valence shell should look like. So if you remember, off-brow says fill up the S before we fill up the P. We have to build up from lower to higher energy levels. And if we did that, we would get this, and then Hund's rule says put 1 in each P orbital before we pair up. So if you look, this carbon has only 2 unpaired electrons, and I have 4 hydrogens that need to form a sigma bond, so this is not going to cut it. So what happens? Well, these orbitals will hybridize. They'll basically fuse to form a special hybridized orbital that one of these electrons is going to go into the empty P orbital to form 4 equal energy orbitals, each with 1 unpaired electron. So let's see that in action. Just strictly looking at the orbitals, the S and P of different energy levels become sp3 hybridized, all of them. Why is it sp3 hybridized? Well, this is what we had before. If you remember, I told you one of these electrons goes over here into the P, so we'll have 3 P's and 1 F. If one of those S electrons goes into the P, then we're going to have 3 that came from the P and 1 from the S to form 4 equal degenerate, meaning equal energy level, hybridized orbitals, each of them containing an unpaired electron that can now bond with hydrogen. So hydrogen can now donate its electrons to form a sigma bond with carbon. Then we get the bond angles of 109.5 and all that good stuff because these are now hybridized orbitals. Because if you look at just purely P orbitals oriented around the X, Y, and Z axes, which are 90 degrees to each other. S is a sphere. So how did you come up with 109.5 as a bond angle? Well, it's because they fused a little bit and became hybridized. So check out the
double bond example and the lone pair example because they do get funky, but use this to always check your work. So memorize this as quickly as possible. But the best way to learn this stuff, as always, is to practice, practice, practice. Thanks for watching. As always, check out the example videos. For best results, pause the example video, attempt the problem, then check your solution. If you got it right, then cool, you can move on. If not, then go back and watch the video and see where you messed up. I hope this has clarified things enough for you to practice a few problems. Thanks for watching. Have a great day.